Alright guys, so let's get started doing this problem from discussion worksheet 6, and let's just jump straight into it. I've already gone ahead and labeled the first part of the problem, which I think most of you got right. The directions are actually given in the beginning of the problem. It says to label the positive x-axis as being parallel to the surface on which the object slides. So for M1, right, it says M1 over here. For M1, draw the axes parallel, and then for M2, draw them vertical. So upwards, and going up is y, and going to the right in this case, if you kind of tilt your head, is positive. It's pretty conventional, pretty normal stuff, so that part shouldn't be too bad. And I've also gone ahead and pre-drawn these limiting cases. So in the case where M2 is much bigger than M1 and where theta is equal to 0, so theta is equal to 0, and over here theta is equal to pi over 2, and I was going to go over that. So pi over 2 is just 180 divided by 2 gives you 90 degrees. And if this is theta over here, 90 degrees would essentially be when this plank is all the way down, right? So just like this, all the way down. Okay, so in the first case, if M2 is really huge, right? If M2 is huge, imagine having a car attached by like a steel cable going over to this super strong pulley, I guess, and you had this really thin and really small object, like let's say a cardboard box attached to it. This car is basically in free fall. There's nothing stopping it except for this tiny little, resistance coming from a cardboard box. So we expect A2y to be approximately negative g. And the reason why it's negative g is because we expect this M2 to fall down, right? Similarly over here, if it's 90 degrees, except this one's the really big one, the angle actually doesn't change much when we go to limiting cases, when we go to extreme cases. So if this object is huge and this one's again a cardboard box and M1's a massive car, and I let go, this cable is basically negligible because the resistance is only provided by this super light weight. So this again is basically in free fall. So the A2y, A2 in the y direction acceleration should actually be positive g. And the reason why it's positive is because we're still considering the acceleration of the second object, but this time it's actually going up. So we expect it to be a positive g as its acceleration. And here's where it gets confusing. You might be wondering, well, this object's not really in free fall. This one's in free fall. Sure, but then if we ask ourselves, what's the acceleration of M1? Well, most of you would say negative g, right? But the acceleration of M1 and M2 are actually identical because of this rope. So this rope is a physics rope, and a physics rope means that the rope is not compressible. You can't you can't bend it. I mean, not bend it. You can't fold it in on itself. Okay, it's kind of like a steel wire in that case, but it also can't stretch. So I guess just like a steel wire. So it can't stretch. It can't be compressed. So if any part of the rope moves with some acceleration, every other part of the rope has to move with that exact same acceleration. So that's why any acceleration that happens to M1 is going to happen to M2. So if this one's in free fall, it has an acceleration of g. This one must have a positive g. Okay, so I don't want to spend too much time on that. Let's go ahead and move on to the challenging part of this problem. The really challenging part is solving for acceleration only in terms of these variables, m1, m2, g, and theta. So the first step in doing these kinds of problems is always going to be to first, in any force-related problem, is to first draw the free body diagrams for the objects. So I'm going to go ahead and erase these over here. And let's go ahead and draw the free body diagram. For M1, I'm just going to draw it here. We have gravity that's pointing down. Okay, so F of G. We have a normal force from this ramp onto the block. Let's call that normal force. And we also have this tension in this positive x direction. So tension. But now we need to figure out the components of gravity. And the reason why it's important to figure out the components of gravity is because we're going to have to use Newton's second law in this problem, F equals ma. And when we do F net, rather, equals ma, to find F net, whenever we talk about the net force, we're always talking about a particular dimension first. Because to find the net force, we need to add up all the forces, right? And you can only add up forces that are within the same dimension. So, for example, if I wanted to see, tension's pointing in the positive x direction, I'm going to subtract it from whatever force is pointing in the negative x direction. Well, I can't know what's pointing in the negative x direction unless I can figure out these components, right? The x and y components. So that's what we're going to do right now. I'm going to break this vector up into its two components. which should look something like this, okay? And now I'm gonna go over real quick how to find out which of these two angles is theta. This one's obviously a 90-degree angle, so it can't be that. But if I extend this dotted line out, right, and then I bring it down over here this way, I formed a triangle over here, right? You can see theta's over here, and this is going to be a 90-degree angle, as you can already see. And if that's a 90-degree angle, let me zoom in actually much more. If that's 90 and that's theta, this angle right here must be 90 minus theta. And if that's 90 minus theta and this entire thing is theta, this angle right here must be theta. And if that angle is theta, right over here, then this angle over here must also be theta. So that's how you do that part. If that confused you, I'd suggest rewatching it a couple times, maybe trying it yourself. And worst case, worst case, if you don't understand that, at the end of this video, I'll go over the limiting case way of doing it. Like, if it were completely parallel, would sine of theta or cosine of theta give you 0, blah, blah, blah. Anyways, I'll go over that. But for now, I have my three forces and I have my two components of my gravity force. So I have Fgy and I have Fgx. And this actually equals mg, right? Because f of g is equal to mg. So the x component is equal to mg, but the sine of theta component. So the sine of theta. And this one should equal mg cosine of theta. Now let's go ahead and draw the free body diagram for M2. So for M2, it's actually quite easy. We only have two forces acting on this. We have the tension pulling it up, so T, force of tension T, and we have gravity pulling it down, so Fg, I guess on 2. I guess I can write over here on 1. Okay, so we have those two forces. Now let's go ahead and just write them down as they are. So we're going to do Newton's second law. F net equals ma. So for the first object number 1, mass 1, we can say F net equals ma. So the two forces for the first object in the x direction are T, tension, going this way. And we also have this x component of gravity going in the negative x direction. So T minus the weight in the x direction. That equals the mass of object 1 times the acceleration of object 1. Okay? And now T is just T for now at least. And Wx is actually just, we already figured that out, the weight, the force of gravity, the weight is just mg sine theta. So we can subtract from here m1g sine of theta equals m1 a1. Okay? And then for object 2, let's do it over here. We have the same thing, except this one's pretty simple. We just have tension going up minus, let me show you guys, minus this weight component, this gravity component, minus the weight of object 2, I guess, equals m2 times a2. Okay? So we have these two things. Now, here's where it gets a little interesting. We can actually say that A1 is equal to negative A2. And the reason we can say this is because, going back to what I was talking about earlier, how the rope cannot be compressed or stretched. If this rope can't be compressed or stretched, if this part of the rope goes down by like a meter, right, this part of the rope has to also go that exact meter. So any acceleration that this object has, M2, M1 has to also have. Except in this particular case, if M2 is going down, M1 is going in the positive direction. So as this is going negative, that's going positive, which is why I wrote that A1 is equal to negative A2. Okay, so now we have these two equations. I'm just going to rewrite this one again without that weight component. T minus M2G is equal to M2A2. Okay, and now for this part, if we substitute for A1 negative A2, here's what we get. T minus M1G sine of theta is equal to negative M1A2. This is probably the trickiest part, is going from here to here with that negative sign, and that comes from this fact. But I encourage you to think about that for a bit. Think about why the accelerations have to be the same in magnitude, but not necessarily in the same sign, and how I got to that. Okay? So now moving on from that, we now have these two equations. Okay, we have this one and we have this one. Okay, so now that we have these two equations, let me just rewrite them again in black. Okay, now if I add these two equations up, okay, or rather, if I multiply the entire thing by -1, just so I can add them up, I get negative t plus m1g sine of theta equals m1a2. And if I add these up, you get these cancel out. Then I can factor out this a2 from those two variables. Then if I divide this out, I'm going to divide this from both sides. Now, my hand is killing me. Let's see what we can pull out from here. Let's see what limiting cases we can test out now. Now let's check to see if these two limiting cases on the left side make sense. Okay, so in the first case, we're assuming m2 is this huge number, okay? And m1 is tiny. So if m1 is tiny, this part of the equation is basically negligible. So is this part, right? So m1 would be really small. You'd essentially just have approximately just this negative m2g, because this part would be basically 0, divided by, again, m2, which gives you approximately negative g, because these will cancel out. So that one makes sense. That limiting case makes sense with this equation. And then the second limiting case is whenever m2 is huge. M2 is huge. Sorry. M1 is huge. When M1 is really big, and M2 is essentially doesn't exist. And when sine of theta is 90. So when that's the case, when sine of theta is 90, we get a 1. If M1 is huge, that means this factor cancels out, and this factor becomes irrelevant. And at 90 degrees, sine of theta is just equal to 1, right? And now we have m1g over m1. These cancel out, and you get approximately positive g, which is what we predicted, okay? So I hope that helped. I hope the walkthrough of that problem helped out a little bit. And thanks for watching, guys.